Yeah, start the live stream also.
Yeah, started.
Yeah, okay. So, good morning, everyone. We'll start with lecture 4 of on astrophysics. And today I'll talk about the life and times of stars. So far, if you have noticed that I was trying to approach astrophysics from the side, from physics side, so that it's a bit more familiar to you. But now I will do it like the way an astronomer would think, and then talk about the astrophysical objects. And I start with the most popular object among everybody, and also the astrophysicists, the stars, because stars are the objects which we know most about, or we understand the most. And that's primarily because, or the starting point of it is because we have the very bright star very near to us, so that we can study many of the properties very clearly. So this is a one-page summary of all that we know about stars, like qualitatively what we know. So stars basically are spherical balls of gases, and they are held together by gravity. They have an internal source of energy, and as you most of you know, that the source is the nuclear fusion. The stars seem to have different colors. When you look at stars, some of them seem reddish, some of them seem bluish. So this is mostly representative of their surface temperatures. They appear to be bright or dim. Some of that brightness that difference in brightness is intrinsic. The rest of it could be due to the distances. If a very bright star is placed very far away from us, the light coming from it dims. So, and the reasons for the difference in their intrinsic brightness, which has got to do with the properties of the star itself, are primarily the differences in their masses and age. And the stars, they are made up of gas, as I said. And what does this gas consist of? It consists of, like most of the universe, mostly of hydrogen and some amount of helium. Like our sun has about 70% of hydrogen and 28% of helium, and all the other elements constitute 2% by mass of the total mass of the stars. So, and the composition of stars, they actually change over time. I won't have time to go into the details of it, but we will see we will understand that why they should be changing, because we have nuclear fusion going on at the center, so new elements are being produced. But however, and the composition is not uniform, because the nuclear fusion is happening at the center, so it's not necessarily that the whole thing is being distributed over the entire star. And however, almost throughout the star, it is a good approximation, and it's and absolutely reasonable to assume that the matter is in ionized form, so that because at such high temperatures, atoms get broken up into ions and electrons. And so here is once again what sort of makes the star takes up the shape that it has. So obviously, throughout the life of the star, it maintains equilibrium between gravity that tends to pull it towards the center, it tends to collapse the star, and any pressure gradient. Now, what is the pressure due to? It could be thermal pressure, and as we discussed, that it could also be degeneracy pressure, which happens for special types of stars which are highly dense. And so this pressure tends to expand the star or prevent the star from collapsing. And in some very special cases where the star becomes very hot, or then, and in turn actually the star is very massive, then the pressure due to radiation becomes important. So the thing to keep in mind is that for most stars, it is the thermal pressure which balances its collapse against gravity. So that is the balance that is there. Now, you all know, and I also say that the source of energy in a star is nuclear fusion. So this energy is being, and how do we know that it is there? Because the star is always emitting energy. So if it is continuously losing energy, there must be a source of energy which is replenishing it. And based on some calculations on how long or for how long the star, say our sun is radiating, and how long is emitting energy, and for how long it has been there, it was concluded, and it was successfully proven that it's actually nuclear burning or nuclear reactions. This is burning means here, whenever I say burning throughout this lecture, I mean nuclear reactions. It is the nuclear reactions which are taking place in the central parts of the star, which is the source of energy for a star. And And in particular, the stars which are burning hydrogen at their cores are called main sequence stars. And it is also realized, we will see a little later, that this is actually the longest lasting phase of a star's life. Like most stars that we see would be caught in a state where they are burning hydrogen at their core, because that is the longest lasting phase. So it's like a statistical experiment. If you keep looking at an ensemble at different instances, you will see the events which have a longer time scale, like which are there for longer. So you have a chance of catching a star in its longest lifespan, the longest stage of its life more frequently. Or so that's why this is so, and this is called the main sequence. Why that is main sequence, we'll come to that. Now, this energy is being produced at the core of the star. How is it being transported? The whole star is, of course, it of course becomes very hot. So there we are aware of three modes of transportation: convection, radiation, and when in the case of stars, this transport of energy is mainly by convection and radiation, and to a very small extent by conduction. So by conduction, you know that they have to be in touch, and then that can happen only if the star is very dense and something like the white dwarf. So a very small amount is like that. Now to understand where we will have convection and where we will have radiation, there is a simple way to look at it. So convection, as you know, is this like where the particles, like the heat parcels as well as the particles in the fluid keep moving inside the fluid and carrying the heat with it. So convection becomes the dominant mode of energy transport when the temperature gradient, that is the temperature between, say, the innermost part of the star and the outer part, the difference in that is large enough so that when a parcel of gas from inside the star starts to go outside, or it continue, or as I'm saying that for, if you consider this analogy, that it continues to rise, it starts to rise, then if the outer layer is cold enough, then this layer, the parcel of gas which is coming from inside being much hotter, will continue to rise. However, if it is colder than the surroundings, then it sinks. So which means that this convective currents will be maintained if the outer layers are cold enough. So that what that means is that the temperature gradient is large enough so that the warm gas which is coming from inside continues to rise and go further into the outer layers. So and convection has not only carries energy, as I said, it also carries material. So that causes mixing of materials inside the star. So that has its consequences. As I said, that the new elements are being synthesized at the core of the star, then they get spread out all over the star, could be to a large extent due to convection. However, if the temperature gradient is not large enough to sustain convection, so that if a parcel which rises leaves the inside of the star, actually drops immediately back, then it's not carrying energy out of the inside in center of the star. So then the main mode of transport of energy is radiation. So radiation will dominate in regions where the temperature gradient is low, and also the energy, also the opacity. Opacity, as I told you yesterday, is something which blocks or absorbs the radiation. But so if energy is allowed to flow freely through the outer layers, then radiation is the main mode of transport of energy in the stars. Now, based on that, so we can then understand that where in the star, let's try to see where in the star should we expect radiation to be the mode of transport of energy, and where convection should happen. So for that, we have here, we have to take things like depending on the masses of the stars. So it depends on the internal structure of the stars. And as I said, that since stars spend most of their lifetime in or the longer part of their lifetime constitutes the main sequence where they're burning hydrogen at the center. So so this internal structure of the star depends on, and this how much hydrogen is being burned depends on its mass. So the internal structure during the main sequence phase is decided by the mass of the star. Now, if you consider a star which has with mass between 0.3 to 1.5 solar mass, then what happens is that we have hydrogen fusing to helium, and but that happens through a chain of nuclear reactions known as the proton-proton chains. Now, these proton-proton chains, they do not establish a steep temperature gradient. And as I said, that we need very large temperature gradients in order to have convection. So in the absence of that, the radiation, the transport of radiation, transport of energy happens through radiation in the inner parts of, say, stars which have masses more like our sun. However, in the outer parts of such stars, they are cool enough because the hydrogen is neutral. And so when hydrogen is neutral, then it means that if you have ionizing photons coming out of the center of the star, they will be spent up in ionizing the neutral hydrogen. So which means that there is a loss of those photons, which means they are opaque to the ultraviolet photons. And this also means that basically there is a temperature gradient which is set up. So in the outer layers, so in the outer parts of the of such stars, convection will dominate. So the one line understanding is that solar mass stars will have radiative cores and convective envelopes. Now let's see how it changes. Let's go to the absolute extreme, where we have a star which has less than 0.5 solar mass, mass of less than 0.5 solar mass. So now this is a very small thing, and basically what happens is that when the energy is being produced, a huge amount of energy is being produced at the center due to nuclear reactions, then basically there is a large temperature gradient because of the smaller size of the star, and so immediately there is no radiation, so the whole star becomes convective. So that is one extreme case where we have an absolutely convective star. Then if we go to the other regime where the stars are more massive, more massive than 1.5 solar mass, there also at the center, hydrogen is fusing to helium, but it occurs through another set of nuclear reactions. And these nuclear reactions are actually, they are called the CNO cycle. And they generate energy at the rate of T to the power 15, that is whatever is the temperature, it's the 15th power of that. So huge amount of energy is created at the center, which means that there is a significant in the inner part of the star, the temperature gradient DTDR is then very large, because the energy created, the temperature created at the center, or the energy created at the center is very large. So for such stars, because once again, it is because of the different kind of nuclear reactions which are happening. Basically the core is convective. However, in the outer parts, this temperature gradient becomes shallower. But if the temperature is high enough, but the temperature will remain high enough. So which means that the hydrogen will be fully ionized. Now, once hydrogen is fully ionized, then there is no opacity for the ultraviolet photons, the photons which can ionize hydrogen, because hydrogen is already ionized. So those photons will just escape can pass through the outer layers, which means that, and so they can radiate through. So which means that the massive stars have a radiative envelope and they have a convective core. Okay, so I'll stop here and take 2 or 3 quick questions.
As of now, there are no questions, ma'am.
Okay, so let me just continue. I'll stop here. Yes.
Okay, just one came up. What is the lower and upper limit of the mass of star up to which it will remain in the main sequence phase?
That I will discuss later. So you see, all of these are main sequence, whether it's when I'm saying this mass of 0.5 or 1.5 and greater than 1.5, these are still main sequence. Hydrogen fusing to helium at the core is main sequence. So we will talk about main sequence stars separately. I will come to that. So next, we come to the something which the astronomers they devised, and this is used extensively to study stars, observe stars, put there, and to understand the properties of stars in one, like in a single shot. Like it's just one single snapshot that tells you a lot about how the stars are and how they evolve as well. We will make use of this diagram. So this diagram is basically a plot of the luminosity, logarithm of the luminosity of the star versus the logarithm of the temperature. One thing you have to know is that the temperature, if you notice, is actually increasing to the left, from right to left, which is in the inverse direction than we are typically used to plotting the x-axis. This is a convention. This is how it was done for the first time. There is no reason, like no physical significance of this, if I may say. So now you know that the luminosity of a star with effective radius effective temperature of T effective and radius of R is given by 4 pi R square sigma T effective to the power 4. Now in this plot, what you can see is that this shows such a plot of luminosity as a function of effective temperature, say of the stars seen in a cluster. What you notice is that a large number of stars fall along a sort of diagonal line which cuts across this diagram, and all these stars are known as the main sequence stars. And they're known as I already said, that the main sequence stars are the ones which have so main sequence phase is the longest phase of a star's life, and we will come back to that. So just to complete the story, so we also notice that there are large number of stars which have a pretty high luminosity compared to the main sequence stars, but they are not so hot, because if you notice the star here and the star here, they have the same effective temperature, but they have much larger luminosity. Now, if you look at the expression for the luminosity, we will see why the luminosity is higher than if the effective temperature remains the same. It is the radius which is higher, and such stars are called giants. I'm saying this because we will be using these terminologies later as well. Now, coming back to the main sequence, now the question arises, why do most stars appear to be on the main sequence? And I already answered to that, because that consists of 90% of the lifetime of a star. So if some phase of your life is the longest, then somebody who keeps meeting you every 10 years will be seeing that phase of your life mostly than the phases which have been like shorter, like maybe the time when you didn't have your milk teeth were gone for 2 months or so, but they will be seeing you with your permanent teeth for the longer period. So that's how it goes. So for astronomers, since we will see that the evolutionary time scales are much larger, they are like millions and billions of years. We cannot follow a single star, but we can always look at a number of stars. But then when we look at them, we will find that most of the stars are in their main sequence phase, and that explains the sort of overabundance of, if I may say, stars which are in this along the main sequence. Now coming to the main sequence stars themselves. So this will be the approximate structure of a very schematic structure of a main sequence star. We will have the core hydrogen fusion, and so just keep in mind that when I talked about convective and radiative convection and radiation, I spoke about that different kinds of core and envelope being interchanged in terms of energy transport, but just the thing to keep in mind is that it's always hydrogen fusion which is happening, irrespective of the nuclear reactions which cause them. So this is the sort of thing which identifies main sequence stars, and they can have different total masses. They will have different radii and luminosity. So here I give you some numbers, and those numbers are expressed in terms of solar mass, solar radius, and solar luminosity, and these are the absolute physical values for those. So now the stars which have masses lower than 0.06 solar mass will have very low densities and temperatures. And as you know, in order to start a nuclear reaction, high temperatures and densities are needed. So they will not burn as in nuclear burn hydrogen. So they are not really stars. So they fall. So, and they are not main sequence stars either. So they will be, so main sequence, you can consider that the lower mass bound could be 0.06 solar mass. And similarly, stars which are very massive, say about 100 times or 120 times solar mass, they cannot exist, because as I mentioned that there are different kinds of pressure which are balancing the star against the gravitational pull. And of them, I mentioned radiation pressure is one, and it becomes important when the star is massive, because in those cases, the radiation coming out of the center of the star is so much that it tends to blow away the outer layers. And this mass limit is called Eddington limit. It is very easy to calculate. You just equate the radiation pressure to the gravity, the force due to the radiation pressure to the gravitational force, and then that gives you that for what mass you will no longer have a stable, the star will no longer remain in the form. So when radiation pressure becomes greater than the gravitational pull, then you can no longer have a star. So this can be considered to be the upper limit of the mass of the star. I think that answers the question that was asked just now. And just to give you some numbers, the radii of the stars, these main sequence stars, vary from 0.1 to 15 times the solar radius for a mass range which varies over by a factor of 2000. And the luminosity actually shows a much larger range. It changes between 0.01, 1/100th of the solar luminosity, to about more than, almost a million times the solar luminosity. So this is the range. What we immediately see is that there's a huge range of values, physical parameters, even the main sequence stars will have. So these numbers look small because we have expressed them, these very large numbers, in terms of these symbols. Okay, so now if you continue, so are there any questions right now?
No, ma'am. No, ma'am. There are no
Okay,
questions.
okay. So so having established what the main sequence is, let's see what happens to the star once it has burnt. It is burning hydrogen, or nuclear burning hydrogen at the center. Now, once it has burned the entire hydrogen, which is at the temperature that can sustain nuclear fusion, then what happens to the star? So first of all, so the exhaustion of hydrogen in the core. So what happens is that then I have a core which is helium. Helium is heavier, and there is no source of energy, so it starts to contract under gravity. But now, as it is contracting, it will heat up, because if it is contracting, it is releasing gravitational energy, and that will heat up the core. And now what happens is that, so we have the central helium core, but we have surrounding it a shell of hydrogen, right? A narrow shell, thin shell, which is in contact with the helium core, and hence has the temperature of the helium core, which is very hot, but not hot enough to fuse helium, but hot enough to fuse hydrogen. So then the hydrogen in the shell starts to burn. That is called shell hydrogen burning, and that happens somewhere here. So this yellow position is where the star starts its life in the main sequence. Then it actually goes a bit towards higher temperatures and slightly higher luminosities along the main sequence, and it is here that it leaves the main sequence having exhausted all its hydrogen. And in this part, primarily the helium core is contracting, and we have the hydrogen shell burning. Now, what also happens is that the gravitational energy which is released by the core contraction, that expands the envelope. So it's not just the near vicinity of the core, but the rest of the star beyond the hydrogen burning shell starts to expand. So the stellar radius increases, and if the stellar radius increases, it means that the outer layers are very far away from the inner very hot part. So which means that the outer layers become cool. So now let's remember that in order for convection to happen, we needed a large temperature gradient. So if I have a very hot inside and the outer layers are becoming cold, that means that I'm establishing a larger temperature gradient, which means that the convection zone, that is, so for such a star, so it will go deeper into the star. So when that happens, because if you recall that we are discussing the evolution of one solar mass star, for which the core to start with was radiative, because the nuclear fusion that was happening at the center was not able to was not able to establish the very strong, the steep temperature gradient required for convection. So now what happens is that, so basically as the star becomes bigger, the surface becomes cooler, and so the radius keeps increasing, and the star goes along. So this goes along means that its temperature and the luminosity change like this. So the luminosity keeps increasing, the temperature almost remaining constant, and that shows that basically it's because the star is growing bigger. As I say, that it's becoming a giant, and such a giant is called a red giant. Now this continues till the core. Now the helium core is contracting meanwhile. So as it is contracting, it's also getting heated up. So now at some point it reaches the temperature where it can fuse helium. So that is the helium ignition point, and that happens somewhere here. So once that happens, once again, it goes back to the sort of scenario where you have core nuclear burning, which means that there is generation of energy at the core. So now then the star, when the helium core is burning, the star comes and settles in this red clump region that is shown here. And so now we have a situation where the helium core is burning, and also we have the hydrogen burning shell. So then the cycle is repeated as it was for hydrogen. because the hydrogen, now the helium in the core will be, all the helium in the core which is at the right temperature for nuclear fusion will get burnt, and so there is an exhaustion of helium in the core, and consequently we will have carbon and oxygen at the center. And the core, then once that exhaustion happens, that core starts to contract and the envelope starts to expand. And that is where, this is the second time when once again the star's luminosity increases, but the temperatures do not increase that much. And this is called the asymptotic giant branch. So this one was the red giant branch. This happened after the helium core was formed, but it was still not fusing. So after hydrogen was exhausted, helium core was formed, we had the red giant branch. Now helium is exhausted there, so there is no core burning. And so basically, so now it is we have a carbon or oxygen core depending on the initial constituents, and then the envelope is once again increasing in size, so that gives rise to the asymptotic giant branch. Now next, what happens to the star when it depends on what is its mass. So for stars which have masses less than 8 solar mass, so what we have to remember, when this is happening, the core is once again shrinking, the carbon core is shrinking. But if the mass is not large enough, then the densities and temperatures never reach the numbers that are required to fuse carbon. So then for stars, the central density and temperatures depend on the total mass of the star. So for stars with less than 8 solar mass, there is no further nuclear burning. However, for stars with larger than 8 solar mass, then the carbon core ignites, and then it is surrounded in the same way by a shell of helium and then hydrogen. And so progressively higher elements will be synthesized in these stars. Okay, so I will stop here and take some questions, and then I will.
Yes, ma'am. So the first question is, on what basis do we actually mark where the core ends and envelope starts?
That is not a very hard. Yeah, so basically these are all based on models that you build. So then, so if you are given the initial mass of the star, or if you're given the mass of the star, then based on and then you let it evolve. Based on that, you have an understanding that what fraction of the star will be convective and what fraction will be radiative. Mind you, we know basically the nuclear energy generation that is happening, the rates of those. So it's all like, you balance energy, you balance temperatures, and then you have a detailed convective model for that. So these are all stellar model based, and they reproduce observations wonderfully.
Okay, ma'am. So the another question is, fusion reaction is taking place and forming heavy atoms, etc. So are there more and more such turns in the HR diagram as metals are being formed?
Yeah, so they're good in, yeah, so let me just, so they are
Yes.
good in principle B, but for massive stars, so as you understand that, so these will be for stars which are more massive, but those phases they happen very fast. So so even these parts of the thing which are sort of shown in a rather exaggerated way, it's hard to catch a star in that phase of its life, because those are much short-lived compared to the main sequence phase. So in principle, they should be happening, but they are sort of overlapping, and the time scales. It's you were told some things about time scales, different time scales. So these are the thermal time scales over which these things mostly happen. So then they will be, and it's a combination of nuclear time scales or fusions. Or whatever. So then and depending on the mass, and if the mass increases, these time scales become much shorter. So it's difficult to track that. But well, I would think that in the models, one would be able to identify those phases. But observationally, no, it's not. It's difficult to understand.
Okay.
Yeah.
One more question.
Please.
So all these hypotheses that are being made, how are they verified? By simulations or just observation of luminosity?
No, so the thing is that these are not hypotheses, first of all. So these are stellar models based on physics inputs. So when there is a difference between a hypothesis and a model, when you build a model, so these are like writing down equations and then putting the correct physical quantities and then reproducing what you are measuring in the laboratory. would you call that a hypothesis? No, you are using Newton's laws. You are using hydrostatic equilibrium. You are using equations for which you have a thorough understanding of the physics. And then you have what the inputs that you are giving is, okay, let me consider that this is the mass. And then let us consider looking at the, so then what you do is primarily you synthesize not only these not only the so you synthesize models which are for different masses, and then you look at clusters which are expected to have stars of different masses, and then you see what you observe. So the Hertzsprung-Russell diagram that I showed was is an observed quantity as well. So if you make the corresponding observation, say this is so for an observer will actually write color. So I did not want to go into the complications. So color is basically the ratio of fluxes measured at two wavelengths when you are observing a particular object, and the y-axis would have been magnitude, which is an estimate, which is basically the intensity of the star. So that is so using that also you get an exactly the same plot, so you can reproduce. So that will be the astronomer's Hertzsprung-Russell diagram. So these are all observationally verified in that sense. So this is, I would say, these are you apply physics laws, you do rigorous calculations using physics, complete physics equations, and then you put in parameters like mass, temperature, density. Actually, you tell the mass, the metallicity, and rest of it actually follows from there. You let the system evolve. Okay, so this is, I think these are all very strong grounds in that sense.
Oh, okay, ma'am. Can continue.
Okay, so now let's come to the low mass post main sequence evolution. As I said, if the mass is less than 8 solar mass, the stars evolve in one way, and if they're more than 8 solar mass, they evolve in a different way. So this one, once again, so this one, as you see, is that this shows that so these plots are sort of theoretical plots. Like observationally, it's difficult to reproduce these so explicitly, but there are traces of it. Now, what happens for such a star is that at the later stages of their evolution, the star loses a lot of mass, because as I said, that the envelope starts. So here, if you consider, the envelope actually becomes larger and larger. So now, as it is going farther away from the star, the gravitational pull of the star on that outer layer of the star becomes lower and lower till it becomes detached. So it can no longer remain attached to the star itself. So there is a loss of mass. These shells are given out, and for a low mass star, so for a low mass star actually ejects about half of its mass in the form of these shells, and which are called, the final product of it is called planetary nebulae. So okay, I can show you. So these are the planetary nebulae. So these are actual images observed with Hubble Space Telescope. So what you see here is at the center, the star itself, and all these rings that you see are the layers of the stars, the outer envelopes, which are released by the star. So this is a mass loss which is happening. And here they are colored because they are being illuminated by the strong emission from the star itself. So there is a sort of diffuse gas in between, and you see these shells. So this is mass which has been ejected by the star itself. The name planetary nebulae is a bit of a misnomer. It has got nothing to do with planets. It's just the end stages of a low mass star, and the entire gas inside of it is ionized. And so basically, so this is, so what you realize is that it's the central star which remains, and the most of the mass is released. Like slowly it dissipates into the interstellar medium in the form of shells, and this initially, when it's close enough and the gas is still ionized, they give these beautiful images of some things which are called planetary nebulae. And these actually, they have various forms. So this is called the red rectangle, and you can see they look like butterflies. It's actually like they're very beautiful, but that's basically what is happening to them. So going back to it, but for stars which have masses less than 3 solar mass, which is another special case, then they are left with the core. So now the envelope is being removed, so they are left with cores which are about 1.4 solar mass. And 1.4 solar mass probably rings a bell, because you have definitely done it as part of your statistical physics course when you did the Fermi distribution. So that is the maximum mass that so ball of electron can have, degenerate gas, degenerate electron gas can have, and that forms the white dwarf. So white dwarfs have to have masses of the order of 1.4 solar mass. So this sort of gives, so what are the white dwarfs like? So they're Earth size. So if you look at the radius, it's like this, and but they have very high densities of 10 to the 9 kg per meter cube, very high surface temperatures, and very low luminosity. So if you look at the H-R diagram, once again, this is where the white dwarfs, where you will find the white dwarfs. Just notice that they are very hot, but they are very, their luminosity is very low. They get heated up because this is degenerate matter, and so that's what causes the very high surface temperature. But then they're very small. That's why the luminosity becomes very very low. So because the luminosity has the square of the radius. If the radius is very small, then even though the temperature is very high, it becomes so small. The luminosity becomes so low. Okay, so I told you about the planetary nebulae. Now let's consider stars which were above 8 solar mass. I said that they evolved differently in the sense that they can undergo subsequent even further nuclear fusion at their centers, and then so for such stars, basically this is the kind of core that you will have. So this point is basically the core. So core, just to signify that the entire star is so big, but then the core where the nuclear fusion has happened is a very small fraction of the whole star, and in there basically what one gets for such a high mass star or old high mass star are successive layers. So this is called an onion skin model. So it's like onion. When you peel it off, you get similar structures for smaller and smaller sizes, right? So but then what do we see here? So at the center, so this hydrogen burning, so this nuclear fusion continues till iron is produced, and beyond that, it's no longer energetically possible to or energetically favorable to undergo nuclear fusion, because previously whenever nuclear fusion was happening, a fraction of the binding energy was being released. So there was, but however, if further fusion beyond iron has to take place, then it requires addition of energy. So that will not generate energy, and so this process does not continue. So with nucleosynthesis inside the star, that is nuclear reactions inside the star, we can produce elements only up to iron. And so here in the center of the core of an old high mass star, what we will see is that we will have an iron core. Then it will be surrounded by a silicon fusing shell. So if you recall that when we had the carbon core after helium burning, we had layers of helium shell and hydrogen shell. So similarly, there will be some narrow parts which will be fusing, say, hydrogen, helium, carbon, neon, and all those things. But the core will be just the iron core. But since the core is very heavy and it's contracting, beyond this, and there are these burning shells, the rest of the star becomes very large. So it is similar to the giant phase after say hydrogen burning had stopped. So now basically the star itself has expanded very much and it becomes a supergiant. So if you look at the numbers here, it becomes obvious to you. So whereas the core is something like 10,000 kilometers, the star itself is 1.6 billion kilometers. And this is more like Jupiter's orbit. So this is a very large number we are talking about. So this is what the structure of the old high mass star becomes. And now what happens to that? So now, what happens is that we saw that for the low mass stars, the stars after they get rid of all the mass in the envelope, they had a maximum mass of 1.4 solar mass. But for the high mass stars, even after getting rid of most of their envelope, the cores that remain are more than 1.4 solar mass. Now this core is extremely dense, and we have discussed that when matter becomes extremely dense, then it becomes degenerate, and this is electron degenerate, because we discussed that basically for stars at all stages, the entire matter is ionized, so you would have electrons and ions. So now but there are more number of electrons, obviously, because you have had higher elements which have been which have also been produced. So now then, so this electron, so it's an electron gas which is degenerate because of the high density, and so but the degeneracy pressure, and it is the electron degeneracy pressure which sustains the white dwarf against the gravitational collapse. But if the mass exceeds this 1.4 solar mass, then the electron degeneracy pressure can no longer support the star against gravitational collapse, and it starts to collapse. But so now the iron core starts to collapse, and then which collapse means that if the densities, central densities become even higher. And then what happens is that then the nuclear structure also gets destroyed, and when one actually has neutrons, and then one reaches the regime where you have basically a core which has neutrons, and at a temperature of about 10 to the 9 Kelvin, and densities as high as 10 to the 17 kg per meter cube, or 10 to the 14 grams per centimeter cube. And it is then the neutron degeneracy pressure which stops the further infall of the layers. Now when it is sort of stopped from, so what happens is that, so it was collapsing until the neutron degeneracy pressure sets in and stops the collapse. So suppose something is moving very fast towards one point, and suddenly the inner parts stop moving. So then the part which is from outside, they actually come and bang against the non-moving part, because those are now sort of balanced against the gravitational collapse by the degeneracy pressure, and so then they rebound, and then the outer layers bounce back, and this bounce back happens in a very explosive manner. That is, it releases a lot of energy and radiation, and so energy is radiation and matter, and this is what is known as supernova. Just notice the term I have called type 2 supernova. So these type of supernovae are also called core collapse supernovae, because the core is collapsing and then the outer layers come and hit the core, when the core just becomes resilient and doesn't collapse anymore, and then so the outer layer just comes and bounces off the core and then goes away and just scatters off, so with a huge explosion. These are called type 2 supernovae. Now what remains at the center after that supernova happens is the core, right? That is what is that is what has resisted the further gravitational collapse. So depending on the mass, if the star was, so broadly speaking, we were discussing stars which are more than 8 solar mass, but if the star, but then as I said, stars could be up to 120 solar mass without being blown away by the radiation pressure. So if the star with the progenitor, like the star which was collapsing to start with, is less than 30 solar mass, then what is left at the center is a neutron star. But if it is more than that, then basically the center core is even more dense, which means that it's some kind of a singularity, and that is what is called a black hole. So what we have produced, we have talked about, and I have been referring to these terms earlier. So we see that at the end states of this evolution of the end states of a high mass star, basically with a supernova, type 2 supernova, the most of the matter is like spread out all over the interstellar medium, and the core, depending on the mass of the initial star, becomes either a neutron star or a black hole, and a spinning neutron star is called a pulsar. So these are the terminologies you would come across very frequently. So that's what they mean. Okay. So now let's just, so now to summarize, what have I told you? So this is sort of a tuning fork diagram, if you may, but this is not actually used in the deep sense. So let's start from the left hand side. We have say the cloud. We will talk about this in the next lecture. Next lecture actually. So we have this cloud. This is a gas cloud, a large gas cloud from which the stars are formed. This star formation process I will do in the 6th lecture. And then depending on the small and large star also refers to their masses, depending on what their masses. What we saw is that the small star becomes a red giant, and then it becomes a planetary nebula, and then it forms that white dwarf. And similarly, the massive star actually becomes a red supergiant, and then it undergoes a supernova. And then depending on what was the mass of this, or rather this star, then basically we have either a neutron star or a black hole forming. So the summary of it is that all stars evolve over time, and their global properties like the temperature, luminosity keep changing, as well as their internal structure, because we are producing new elements. So there is a layering, there is core burning, there is shell burning of different elements, and so on, like nuclear burning of all of those. And as the star evolves, its brightness, surface temperature, etc. change. Now the time scales over which the stars evolve, for the very massive stars, they are more like few million years, whereas for the lower mass stars, it's few billion years. So the massive stars actually go through their life much faster, because they're burning everything, they're collapsing faster, they're burning the nuclear fuel faster, so everything happens faster. So it's difficult to observe the massive stars actually, to catch them at the different stages of their lifetime, whereas the low mass stars are actually slowly going through the same phase. So it is easier to catch them, in the sense that you have a higher chance of seeing a star in a certain stage of its life. Obviously, the main sequence phase is the largest, and during their lifetimes, these cores of the stars become hotter and hotter, and they produce progressively heavier elements through nuclear fusion, and that stops at iron. And finally, the main thing to take away from this, whatever I have said so far, mass is the single most important quantity which determines the life, evolution, and ultimate fate of the star. So whatever I say was in terms of mass, and these are high, like these are very highly corroborated with physics models based on proper physics, including like hydrostatics, and nuclear physics, everything, all sorts of inputs go into this. And finally, what is the mass of the star decides how the star will evolve. Okay, so this is this is the summary of evolution of single stars. So once again, as I said, I had said in the previous lectures, you may or may not have noticed that. So here I am talking about a star which is evolving in isolation. So let me just take some questions, then we will see how a star evolves in a binary.
Yes, ma'am. So one question was, why are there no elements beyond, beyond iron?
Okay, so this is a nuclear physics question. So if you are aware of the concept of binding energy, so that is the energy that you need to put in order to sort of disperse a neutron, and but then nucleus. But then also when you put two nuclei together, then their combined binding energy for up to a certain mass number of the nuclei becomes smaller than the binding energy of their individual. So which means that if you put the two together, you will actually be able to create the higher heavier nucleus and release some energy. But that happens. So you have to look at the binding energy as the curve for the binding energy as a function of the mass number. And what you will see is that it increases till it reaches say from iron and nickel, but beyond that it flattens, which means that beyond that it's no longer energetically possible to put two nuclei together without adding some energy to it. It does not give out any energy, so the fusion requires addition of energy. I think a sort of related question would be, so if we could just only create up to iron, where did the other elements come from? Maybe I'll ask this question at the end of the lecture if I have time. Then maybe some of you can tell me if you have heard about that. How did the heavier elements coming?
Uh, there is one more question. I don't know if this is off topic, but what are brown dwarfs?
Yeah, so no, it is not off topic. So brown dwarfs are actually stars which do not have they are below this 0.06 solar mass, so that they are sort of failed stars, if you may call them. They are the ones which could not ignite or fuse hydrogen, did not become hot enough to fuse hydrogen at their center. So this is a very good question. So I did not go into the sort of more names. So when one is studying the formation of stars, one also studies the brown dwarfs, because they also tell you, because you are using some cloud from which all the stars are forming, the ones which are sort of bona fide stars like hydrogen burning stars, but then brown dwarfs are the ones which did not materialize. But you have, when you try to develop a theory, you also have to take into account them. Like when you are studying formation of stars, you take into account the brown dwarfs. Brown dwarfs can be observed. There is a whole an entire field of astrophysics which are dedicated to the study of brown dwarfs, and that particularly pertains to the formation of stars rather than stellar. Okay, so I'll continue then.
There is
Yeah.
one related question to brown dwarfs.
Yeah, yeah.
Are these names like brown dwarfs related to the surface temperature?
No, dwarf really, so surface temperature, yes, brown is because of that. Dwarf means it's small in size. So giants are big, dwarfs are small.
Okay,
Okay,
thanks.
yeah. So now I just finished talking about the evolution of stars as single stars. So there was no influence. So I just had a ball of gas or of a certain mass, and I was trying to see what happens to it as it remains it remains for when it remains for some time. Then we have various things. So the stages of the life of a star were for a single star. But now we know that actually a significant fraction of stars are in binary. So this is observationally seen, that you see at least, actually in some cases it's more than 50% of the stars are seen in binaries. Obviously initially people didn't know this, but now with improved observational techniques, it is possible to, it has been understood that there are a large number of stars which are in binaries. So when this happens in the binary, which is sort of what is called a closed binary, what happens is the stars the evolutions of the stars become different from the isolated stars. Now, going back to say my first lecture, if you recall, I had talked about a two-body motion. So then I had said that it could be a binary consisting of two stars, or it could be a star-planet system. So the dynamics or the Newton's law equations of motion that you would write out are exactly the same. So in a binary system, what happens is two stars they rotate about their center of mass with some angular velocity, and then we discussed all this, that if we are in a frame of reference rotating with an angular velocity of omega, then the two stars will be at rest. And then if you recall, we did all the Lagrange points, etc., like for any other point in their field, etc. Now the force acting on a particle, so if you consider any particle which is at any point on in this system which is at rest in this system, it will be the sum of the gravitational attractions of the two stars and the centrifugal force. So just refer to slide 17 of lecture 1. I have written down the expressions for that. And then we also did, like, when we tried to find out which are the positions for which the force, net force acting on the particle disappears, and we called them the Lagrange points, so L1, L2, L3, L4. And in that context, I had also defined something called the Roche law, which Roche law was, so because we have this kind of a system. So basically, if I have, so I had, as I had described earlier, so when we have a point which is somewhere here, then depending on the relative ratio of the masses, we would understand that each of these two bodies, M1 and between M1 and M2, would have a larger influence. So what we had seen was that one can always define a radius around, say, the smaller body, over which the gravitational influence of the smaller body is more than the gravitational influence of the larger body. So which means that each small body, like a planet, or means planet can describe has a sort of small radius around itself, where its influence is most on its gravitational influence is more than the larger body in the system, which is a star. So for a binary star also, that the same thing happens. I had shown this. So this is called a Roche law, and alternatively it's called Hill radius, say, for a star planet system. So Roche law is basically the region around the star in a binary system within which the orbiting material is gravitationally bound to the star. So now what happens? So now let us consider. So this is a very nice, I think, figure which I've taken from Wikipedia. You are most welcome to see this. So now we have two normal stars which are in a binary pair. So they are moving about each other. So now what we know is that, so as I said, the more massive star evolves faster. So it becomes faster, it reaches its giant phase. So once it becomes large enough, so then what happens is that when it becomes larger and larger, but if it exceeds its Roche law, then it is under the influence of the material which is beyond its Roche law, is under the influence of the smaller star. So here it is a white dwarf, but just consider two stars here. That is what in the first case, that is what is happening. So the more massive star becomes a giant, then it spills onto the secondary star, and then that star also expands, and the two basically so it sort of eats up the second star. So the two cores remain, and the two of them basically spiral towards each other, spiral within a common envelope. So the larger star sort of overflows and sort of takes over the smaller star, and creates a common envelope within which the two stars are orbiting. But then this common envelope, what happens is that beyond a certain point, it's no longer it becomes the gravitational pull on it becomes like weaker, and so it is ejected, and basically and the separation between what happens is when this is ejected, the two cores actually come closer, because just to conserve the momentum. So they come closer. So then they are in a much smaller, like closer orbit. So now what we have is that we have the larger star here has what has become the larger star actually has become a white dwarf, and this is the smaller star now. So just keep track of the colors. Initially the white star was the more massive star, which here has become the white dwarf, and now the yellow star, which was initially the less massive star or the younger star. So now but now they're moving in a much closer orbit, and so now this aging companion. So this one is now older. It starts to swell much like this one, and then it starts to spill over its Roshlov and put its mass onto the white dwarf. But the problem with the white dwarf is that the white dwarf, as you know, is a degenerate. It is sustained by degeneracy pressure. So basically, what happens is that if the mass which is put on the white dwarf exceeds its critical limit, so it can no longer it no longer it can bear with it, and then it undergoes something that is similar to what the neutron star also does. So basically, but what happens is that it explodes, because of the additional mass that has been put on it. So I won't go into the details. So basically, if it exceeds the critical mass, then the white dwarf itself it explodes, and leaving behind so basically, and what causes is that it causes the companion star to be ejected, and this whole energy of the white dwarf is pumped into so this explosion is a huge explosion. It's a supernova. So but this type of supernovae are called supernova 1A. One beautiful thing about this supernova 1A is that, so what we understand is that they are now created by the complete annihilation of white dwarfs, which have masses which are still almost close to 1.4 solar mass, which means, so now if you consider that this entire mass has been converted to energy, so which means that the supernovae 1A, at the very onset, they give out the same energy. So this, I will not go into the details. This helps us to use these supernovae as distance indicators, in the sense that we know how much energy they gave out at the point of when they exploded, because that is equivalent of the mass of 1.4 solar mass. That was the mass of the white dwarf, which actually exploded and got completely annihilated. So what you see here is that the evolution, so this is very different from the type of evolution I spoke about, because none of the stars is allowed to sort of go through the phases that I described earlier for a single star, because there is an addition of mass from time to time from its companion. So they move in a slightly different manner, but all of this is understood, and that's how it is. So stars which are evolving in a binary, they evolve very differently from stars which evolve as single stars. So now I'll put up the summary slide, and this is what we have discussed. So if we consider the low mass stars, maybe less than 3 solar mass, they do not burn elements heavier than helium, and then they shed their outer envelopes slowly, forming the planetary nebulae. And the electron degeneracy pressure supports the carbon-oxygen core against gravity, and they have masses that correspond, that is the Chandrasekhar limit, 1.4 solar mass. And these cores then cool slowly over billions of years, and these are the white dwarfs. And as for the high mass stars, they actually burn progressively heavier elements in the core. So here I've written 3 solar mass. Okay, you can consider. So 8 solar mass is what. So that's what. Yeah. So it's like more than 3 solar mass. This starts happening, and so it burns progressively heavier elements in the core. Then the electron degeneracy is not enough to fight gravity, then basically you have the supernovae, because what we discussed, that you have actually this should be yeah, so electron degeneracy will not be enough, it will collapse further, then you will have neutron stars forming, and then there is a catastrophic sort of bounce back, and then supernovae, and depending on the star's final mass of the star. So this refers to the final core. So this whether this is a, when it is between 3 to 8 solar masses, then the final core becomes a 3 to 8 solar mass thing, then that is a neutron star, and if it exceeds 8 solar mass, then it's a black hole. So these numbers basically correspond to not the first star, like that's there I had referred to numbers like progenitors of like 30 solar mass or greater than less than 30 solar mass, but this is the final core that is formed. So these are the numbers for them, and so that's the final stages. So that is how, so this is the summary of all that I have said right now. This is once again the summary of mostly the evolution of the single star. And as we saw for the binary stars, they're similar but slightly more, slightly different because of the intermittent mass transfer. Okay. So I'll stop here and take questions.
Yes. So there is one question. I had read that this process of mass transfer in binaries prevent the more massive stars in binaries to mature. They keep losing mass each time they try to expand. Can you please explain this?
Yeah, so means broadly speaking, that is obvious. Like you cannot form a supergiant, because then it will exceed if it exceeds its Roche lobe, and there is another gravitating body nearby, the mass gets transferred. Whereas if it is growing in isolation, then it will grow to a certain extent, and beyond that, what will happen is that if it's it will just, this shell will be released. So that is the difference. So um, could you just repeat the question? So what exactly is the question, that it doesn't allow the evolution
Yes,
of the
it
star?
doesn't allow the evolution of the massive star.
Well, it does allow, means in the, I don't know how it will prevent. So mostly, well, I have to think about it. Like you give absolutely correct answer. I do not want to. Yeah.
Okay, there is one question here in YouTube which says, so what happens to the neutron stars after they, lose their energy? I mean, what is the fate basically of
Well,
neutron
they
stars?
are there. We keep observing them. They keep spinning their pulsars. So they are there. So sometimes they are in binaries, they still could be in binaries, so neutron. So that's how it is. Neutron stars are observed, so they become much cooler in that sense, and they remain there. And but then in their pulsars, they have other properties. So, like white dwarfs are obviously also there. So they're like the sort of graveyards of stars if you look at them. Like that. So it's like the black holes. They are also. So such black holes are like stellar mass black holes. Yeah.
Okay, I think that is it for now. Uh, yes,
Okay.
ma'am. So,
Okay. So thank you. So anyway, you write down the chats on.
yes, ma'am.
Yeah. So then I can answer them later, and I will respond to that question. I think I have to think about it a bit more rather than
Okay,
evolution of IMAS. Okay.
yes.
So I'll stop
Okay.
sharing, and thank you, Pritesh.
Yeah, thank you, ma'am. Students, you can post the questions in the chat boxes.
You can stop the streaming and the recording.